So let us start. Yes.
Yes.
So our first speaker of the day session is Amram Meirav. She's from Israel, from Shammon College of Engineering, and her talk is on the connection between algebraic, geometric, and topological methods in the classification of algebraic surfaces and curves. Please, Meirav.
Thank you very much, Sergey, and all you organizers for this amazing platform, for giving me this possibility, this platform to give a talk and to share with all of you guys some nice ideas about algebraic surfaces and algebraic curves. I would like to say to you that I dedicate to you organizers these beautiful colors of blue and yellow along the talk. And I want to tell you that you are very brave, and I admire you for having this yearly great conference each year, and I'm so happy to participate in it each year. So thank you very much for this. Now, I would like to tell you that classification of algebraic surfaces and curves are two directions, although we use also similar, not the same, but maybe some here and there, but similar methods, also different ones, of course. And I would like to show you today these two directions of research. So, first of all, I will give some background. Then I will show you some nice examples and pictures. So the goal of the research is, of course, classification of algebraic curves and surfaces. Now, we all know that the classification of algebraic surfaces, also of algebraic curves, in particular branch curves, because we project surfaces onto the projective plane, it's a very interesting question. Okay, it bothers many mathematicians around the world. And I will also give names, references about this. And fundamental groups are very nice invariants of the classification, also of curves and also of surfaces. So, about surfaces, we start with algebraic surface S, and it is embedded in some projective space. Now, I would like to have this. Yeah, okay, good. Let me just take this color. Yeah. So we take S in some projective space, we project S onto the projective plane CP square. And then we get a branch curve C in CP square. Now, C can tell us many things about the surface S. For example, how many singularities we have, what type of singularities we have, and so on. So it's very important information corresponding to fundamental groups. Now, I would like to define the fundamental group of the complement of C in CP square as G. Okay, this is the notation. Please remember it along the talk. So what is nice in C? What is nice in G? That this group does not change when the complex structure of S changes continuously. So all the surfaces in the same connected component in the moduli space, they have the same G. So therefore, it's a very nice invariant. But if we would like to have, for example, some curve C, okay, and it's very hard to describe or to draw a picture of C, then we are also stuck with presentation of G. Okay, I mean, they depend on each other. So I would like to suggest here some older methods, but also new methods to overcome this complexity. Now, the methods in the classification, the new ones at least, are some softwares. So let's say in general that there are methods that can assist us in classification. For example, all of us, some of us use topological classification, some of us use intersection theory or singularities or cohomology or symmetric groups and so on. Okay? But the algorithmic methods, they are dependent on what we choose. For example, it depends on the specific properties of the surfaces or curves that we choose. Secondly, it is dependent on the desired level of detail in the classification. This is number 2. Or thirdly, it is dependent on the preference of ours, okay, of our needs as researchers. So the mathematical community uses usually Magma, Singular, Maple, and so on. I would like to show some advantages of Magma right now, okay? And also 2 self-constructing softwares that were constructed with Sinichkin. So, about Magma, and I will explain to you right away why I put this nice jet here. Magma can simplify presentations of groups in general, but of also fundamental groups in particular. And we get a presentation by means of generators and relations. So we get a list of generators, a list of relations. What is good in Magma is the fact that it eliminates generators from the presentation. But we must remember something, that Magma is smart, but maybe not as sophisticated as we are, because after using Magma to simplify some presentation, then we need also other softwares or other methods. It's like to take a jet somewhere else, and then we need a connection to our final destination, okay? So it's not the end with Magma. Now, let's continue. I continue with surfaces. So there are 2 directions of research on planar deformations and non-planar deformations. So what we do is the following. We take a surface S, you can see here in this yellow diagram. Okay, we take a surface S, we project it onto the projective plane, CP square, and we get a branch curve C. But it's very complicated to do this because I cannot draw a picture of C. So what I do is I degenerate S to S tilde. This is a degeneration, and then we project it onto CP square to get C tilde. So you can see here in this blue picture that it is a degeneration of some surface. In this case, it is a CP1 times a complex torus, because very easily to think about this, that this is the first CP1 and this is the second CP1 taken twice, okay? And this is a torus, because we can degenerate torus to somehow to a triangle. So you can see that we have some identification here. Okay, when we identify both sides, right and left, we get some cylinder. So it's non-planar degeneration. But the fact that we can divide it into these triangles, this is the full degeneration. So what happens here is that we get, actually, if we project it onto CP square, we get C tilde, which is a line arrangement. You see all these lines? This is actually the line arrangement. Okay, this is C tilde. Now we have a deal with line arrangement. And then we regenerate it in order to try and to recover the branch curve C. So I cannot enter now to details about this. I just methods that we use, but I want to concentrate on the new results and the new methods. This is just a part that we use always, but it's older. It's older thing. And this example was taken from some work with Tan, Shiu, and Yoshpe. You can see here. But the question is, what do we profit from the generation? The answer is that when we try to write down a presentation for the group G, then we draw a dual graph. And the numbers representing the triangles are now the vertices of the edges in the dual graph, because we can draw the dual graph like this. Okay, you see? Something like this. And then what we profit from this is a correspondence to the symmetric group, because each line, for example, 12, if we draw the dual graph of G, this will be this line, which connects both triangles. And then, for example, 12, the generator 12 can go to alpha beta, a transposition in Sn for alpha and beta, the numbers of the triangles. So it's very nice to deal with symmetric group, of course. Okay, we know how to play with this. We took basic courses, and most of us know how to deal with symmetric groups. So it's just convenient to work with this language. Now, very important to say, guys, that good references for learning these deformations are Calabri, Chiliberto, Flamini, and Miranda. And now, group G can be also very complicated. Why? Because of the types of the singularities. Also, high multiplicity of singularities. For example, if you look at this point, you see that 6 lines meet at this point. So when you want to regenerate it, it's a big deal. But we have something like a dictionary. Okay, we succeeded to dictionary of how to regenerate all possible degenerations. Now, if there is a problem, if our group G is complicated, then we can find the G Galois. This is the fundamental group of the Galois cover of S. And this is also a nice invariant of the surface. Just as an example, this group, if I want to compute from this one, a group G, okay, G will be generated by... Oh, I'm sorry, something happened with the Zoom. Can you hear me?
Yes, now, yes.
Okay, I don't know what happened with the Zoom, I'm sorry. Okay, I just say that this picture corresponds to the surface T times T, where T is a complex torus. And here we can have a very complicated fundamental group G. And it's not so worth to compute G in such a case. It's better to compute G Galois. Okay, I will continue. I think there is a bit of delay in the Zoom, because now it's okay, because I changed already the page and it was still stuck because I can see on the other computer my shared screen. Okay, now it's okay. Now some results on planar degeneration. For example, we have studied a planar degeneration with RK singularity. So we take all the surfaces that degenerate to such degeneration. You can see here one RK singularity, okay? And we succeeded to prove that the G Galois, the fundamental group of the Galois cover of the surface S, is trivial for any K. This is a joint work with Gong and Mo. Now, recent research with Gong and Mo, okay, focuses on some nice generalizations. So the generalizations correspond to planar degeneration still, okay, but they are interesting enough because there are some constraints. I will tell you right away. So the first generalization is to take Galois covers of a union of Zapatic surfaces of type RK. What do I mean by this? That if we succeeded to prove about this degeneration, now we glue such two degenerations for any K. You see here, we glue them, okay? And we succeed to show that the Galois cover of such union of such Zapatic surfaces with RK singularity each is this Galois cover is simply connected. It means that the fundamental group of the Galois cover is trivial. So that was very nice. So no constraints, but this one has already constraints. The second generalization, it's a deformation of Zapatic stable surfaces. This is a joint work with Gong and Mo and with appendix of Janusz Kolar. So you can find this paper on the archive. So we succeeded to prove that the Galois covers of these surfaces are all simply connected. So the fundamental group is trivial for n from 4 to 9. But if n is bigger than 9, then such surfaces do not exist. So most of you know such surfaces as EK singularity, okay, like this. And now some results about non-planar degeneration. So we study non-planar degeneration of degree 4, 6, and 8. For example, if I just enlarge the pictures to see, okay, like this, and you see that if we glue the edges along the numbers, along the same numbers, for example, 4 to 4, 3 to 3, and 5 to 5, then we will get something which is non-planar. Or these two pieces, these two planar pieces, if we glue them together along the external edges, we will get some triangle pillow. Or if we take these two pieces and we glue them along the 4 external edges, then you can see that we get also some square pillow. And you can see the results here. Okay, still we cannot see some generalization for these cases. These are the first generalization, the first computations for non-planar degenerations, but we still cannot see really some generalization. We continue to think about this. Okay, now, how do we do all this work? So here are the main steps of the work. So when we get, by the regeneration, the branch curve C, we can use the Zariski-Van Kampen theorem for cuspidal curve because we end up with a cuspidal curve because of some regeneration rules. And we get some list of relations. For example, if we have a conic like this, then we will have an equality. If we have a node, then we will have a commutation relation. If we have a cusp, then we have some triple relation, which means ABA equals BAB. We have also the projective relation in number 4. The projective relation, it means that we must add the product of all the generators is the identity. And also some, number 5, some commutation relations for edges that do not meet in S tilde. This is S tilde, but when we project it onto CP squared to get C tilde, the line arrangement, they will intersect. For example, if you look at edge number 12 and edge number 6, they do not intersect now. but when we project onto CP², they will intersect, so we add some commutations to our presentation. So it's a very long and complicated presentation for the group G. Now it's the time to use some software. So this is already something new that we use also for plane curves. Later on, I will explain. So the first software takes equations of all the components in the branch curve C. We put it into the software, and then we get the picture, and we get the presentation of G. Okay? After we get the presentation of G by the first software, we consider a quotient by the squares of the generators. I will explain later on why it's nice to take this quotient, and we put it into magma. So here you can see some screenshot of the input into magma, and after we run magma, we will get a simplified presentation for this quotient. Now, what is nice in this, that after we get this simplified presentation of our quotient, is that the G-Galois, the fundamental group of the Galois cover, is actually the kernel of the map to the symmetric group Sn. N is the number of the triangles in the degeneration that I showed you before. Now, traditional manual simplification is not recommended now, because although we used magma, as I say, it's not so sophisticated as we think. So we turn to the second software, and for this we need some correspondence to Coxeter group. So very, very quickly, some information about Artin and Coxeter group. We follow a work with Lawrence and Vishna about this, that we define Artin group AT, as usual, as we know, that the edges of some graph are the generators, and the relations can be a triple relation or commutation relation, or it might happen that we have two edges meeting in the same two vertices. It might happen in our cases, of course. Then we define some quotient AYT to be the quotient of AT. Then by some specific relation, but because of a short time, I cannot give you all the information about this. If you are interested, of course, later on, you can contact me in private to see the right definition. So we take our quotient AYT and project it onto CYT, which is a quotient of the Coxeter group CT by the squares of the generators. And we know by that joint work that this quotient of CT, which I call CYT, is isomorphic to some very nice semi-direct product of the symmetric group Sn with some specific, very special group FTN, which is very, very convenient. Again, I cannot give you all the information now, but I can interest you in this later on. Just to tell you what is N and T. N is the number of the vertices in T, and T is the number of the cycles in T, because we have also many cycles in the dual graph. And the generators are very nice ones called UIJ. Okay, so the second software that we constructed gives us as an input the relations of our quotient, of this quotient, by the language of CYT. There is like a correspondence between our quotient to this CYT in the language of this semi-direct product. Why? Because it's convenient to work with symmetric groups. Okay, so, and why are we allowed to use them? Because in all the examples till now, it worked out. It worked very, very good. And you can see that when we draw a picture of a dual graph, you can see the correspondence between some edge and the vertices. So it's very nice and convenient to work with this because anyway, the work is very complicated. Calculations are very complicated, so we must find something which is easier for us. So this is a screenshot. You can see a screenshot of the output from the second software. You can see that you play with the transpositions from the symmetric group, okay? And so this is more or less what we do. So an example before I turn over very quickly to algebraic curves is that if we take, for example, these two pieces in the orange color and we glue them together along 5 and 6, then we will get something which is non-planar, okay? What we do is that after we simplify our quotient in magma and we get a dual graph, a dual graph, let's say, okay, we can define our correspondence to CYT, but we know, according to that work with Lawrence and Vishna, that there is this isomorphism to the semi-direct product using this software. So actually, to summarize this example is that we have these two maps and we need to compute the kernel of this decomposition. But in this specific example, only, of course, in this specific example, the software that pulls back these defining relations from our quotient to the semi-direct product provides us that all the generators in F18 are contained in the kernel. So it means that our quotient is isomorphic to the symmetric group, and therefore the jiggle Y is trivial. So if you want to see the full description of this calculation, it appears in one of the papers on the archive. You can turn to me and I can direct you there. Now, a few words about algebraic curves. So in algebraic curves, these algebraic curves, they are not connected to algebraic surfaces. Okay, you can classify algebraic curves with no connection to algebraic surfaces. So how do you do it? You do it according to Zariski pairs. You work in Zariski pairs. So you can, for example, classify line arrangements or conic line arrangements. Now, good references are Dektiarev, Artel Bartolo, Pogoludo, Tokunaga, Banai, and Shiran. Also Shimada, Oka, and Carmona. Okay, very good works and a lot of information there for many years. Now, I cite here exactly the words of Ichiro Shimada, that a pair of complex projective plane curves of the same degree is said to make a Zariski pair if the singularities of them have the same topological type, while their embeddings in the projective plane are topologically different. And exactly what Artel Bartolo says, I mean, all these definitions of Zariski pairs are more or less equivalent, okay? So you can choose with which definition you want to work with. So I will give definition of Artel Bartolo. We will say that two curves C and D are members of a Zariski pair if, one, there is a degree preserving bijection alpha between the set of reducible components of C and D, and there exist regular neighborhoods of TC and TD, okay? I mean, these are the neighborhoods of C and D, such that these two pairs, I mean, the curves and the regular neighborhoods of them are homeomorphic, and the homomorphism respect the bijection above. And the second condition is that these two pairs are not homeomorphic. So you see that they are more or less equivalent. And now we work in this thing that some results, but before this, what is the rule that we work with? So the rule is the following. If two curves, say B1 and B2, have the same combinatorial type and different fundamental groups, because we work, of course, with fundamental groups, then they form a Zariski pair with non-isomorphic fundamental group. So you must write, when you work in such case and you calculate fundamental groups and you determine fundamental groups, you must write this sentence. Okay? These two curves, for example, are Zariski pair with non-isomorphic fundamental groups. You must say it. Why? Because if we have a Zariski pair, then it does not apply that we have a Zariski pair with non-isomorphic fundamental groups. Okay? For example, if you take a work of Gureville-Ball, he worked on some line arrangement and he proved it. So we need to be careful how to write that we find Zariski pair. Some researchers work with fundamental groups, some other ones prove it via other geometrical characters and so on, or properties. And now, recently, an example of a new Zariski pair of degree 8 was found in a joint work with Schwartz, Sinichkin, Tan, and Tokunaga. These two curves, you can see them, this is B1 and B2, they are both of degree 8. Both have 3 conics. You can see some of them are tangent to each other, some of them intersect one another, and we have 2 lines, so altogether degree 8, okay? What is interesting is that you see that we have exactly the same type of singularities. We cannot change the type of the singularities. For example, if we know that we have here these tangency singularities, we must have them here as well. Okay? So with the same line, with the same conic. Okay, this is very important. These are the rules, so we need to be very, very careful. So now, for example, we try to make a big tree, and how we divide all the cases. It's very, very complicated because you must make sure that you know all the that you keep the rules of Zariski pairs, or you keep the rules of correspondence from one picture to another. But it doesn't mean that you will have Zariski pair. It just means that at least you classify in a way that maybe you can find Zariski pairs. You also cancel some cases that are the same as other ones. Sometimes when you try to classify, you reach to the same picture. Probably some of you tried to do things like this. So in this case, for example, we got very, very complicated results, but we showed that there are these two groups, the fundamental group of the complements are non-isomorphic, very complicated through some semi-direct product with diedral groups and some Coxeter groups, some Coxeter covers and so on, so very complicated. So usually we also need some help of algebraists. So if you are interested, you can contact me, and it's nice. And this is for now. This is my talk to you. So before finishing the talk, I just want to interest you that if, of course, for any question, for any discussion, you can contact me freely. I am always available. And also we look now for postdocs position and PhD positions, some cooperation with Israel and Germany. So you are welcome to contact me anytime you want.
Thank you very much, Meirav. Thank you. Let us send the speaker. Please, questions, comments, remarks. May I ask you? So what you are doing, it's like the problems in theory. So when you have a node, in a node theory, so when you have that just a closed circle in S3, and we study the topology of the complement, and the homotopy type, and the fundamental group, or something like this. And here you take actually surface in a four-dimensional space, yes, in CP2. Okay,
Yeah.
it's two-dimensional. Well, and you study similar things. You study the topology. And the question is, maybe I don't correctly understand. So there may be several connected components in the complement, or it is usually connected. The component for this.
I cannot hear you, Sergey. Again, no, you are on mute. I'm sorry, you are on mute. Yes. The complement. I heard just about the complement. What did you say, please, about the complement?
In CP2, yes, you consider the
I'm sorry, I cannot hear so well. I'm so. Can you please post it maybe on the chat, or I cannot hear so well because I think my internet is not so.
The question is how
No, it's very important for me, but maybe if someone, because the internet, if someone maybe can repeat the question or to say to me this, the internet is not clear to me. I'm sorry. Oh, now I can see. Oh, yeah, I mean, again, it depends. It depends. It depends on the on the surface, because when we regenerate, it depends on the number of the singularities. It's like to do when you regenerate, each singularity will regenerate to a curve, like to a local curve, but all the curves together, they interact with each other. So I cannot tell you a definite answer. I mean, it depends on the example that you take. Because, for example, if you have something like this, Sergey, you can see my screen, yes? Yes. For example, if you take something like this, so for example, this line, okay, this bold line, it belongs to this point, and it belongs also to this point. So everything interacts with everything. So it's very hard for me to tell you what happens there. What happens there? I can tell you, for example, how many conics we have, how many lines we have. I can tell you what intersect with what. I can tell you which type of singularities we get, and so on. I can tell you the equations of all the pieces in the curve, but I cannot tell you, I think I cannot tell you the number of the components. I'm not sure I can tell you this.
So, in that case,
Meirav, you can see chat.
Oh, okay. Okay, I will see the chat. 1 second, yeah.
So the question is,
Yeah. Yeah, this is, I can see, yeah, I can see in that case, the fundamental group of which component,
so you study several So when we consider the computer representation, about which one is going to be. So which one can we choose?
Of connected components. One second. So the first question is the fundamental group of which you study. And the last example, do they you mean which examples we take? You yeah, I see a question, the fundamental group of which component you are studying. This one or number 2? You mean the last example, this one? When you say the last example, do you mean this one? Oh, okay. Have the same number of connected components. Yeah, it must have. It must have. It must have, yes. Actually, I want to tell you about this, that Tokunaga studied some of these pictures. So he could prove about degree 6. About degree 6, he could find some results about the Ritz-Keeper. So what we did is that we took these pictures and we added lines because we wanted to investigate conic line arrangements. So basically, if you look at these 3 conics, this is from Tokunaga's paper. It's nice to see there. And these lines are the additions. But it's also it's not trivial. It doesn't mean that if degree 6 only, for example, with conics are the Ritz-Keepers, it doesn't mean that degree 8 is Ritz-Keeper.
Okay.
Very complicated, yeah. I mean, we can compute it through a fundamental group, but if you want to use other methods, then you don't know anything about fundamental groups.
Okay, thank you very much, Meirav. Thank you. You both hear me.